Okay, so uh, we started this QC of the CVD data, and then we mentioned that there are two kinds of QC, like two types of material balance. One is forward, and the other is backward material balance. We already covered the backward material balance QC, at least how it can be done, and some important concepts. The next material balance is this forward material balance uh, for doing the material balance QC of the CVD data. So what forward material balance does, it is actually an overall QC of the CVD PVT data because it uses almost all the information that's reported in the CVD data, like for example compositions. It requires, for example, gas Z factors reported at each pressure state. It also uses the relative oil volume at each pressure state. So that's why it's, it's using almost all the data that's reported in the PVT report, and it's an overall QC of the CVD PVT data. So since, like, as I mentioned, that it's using the relative oil volume at each pressure state, so that's why it's the accuracy of the material balance. So accuracy of CVD material balance is very sensitive to accuracy of VRO measurement. Okay. And the reason is that because in this QC, what you will see that we will be calculating the equilibrium oil composition at each pressure state. And the equilibrium oil composition is a function of many things. One of them is this relative oil volume, and if relative oil volumes uh, are not accurately measured, then they may cause even negative mole fractions of the calculated equilibrium oil compositions. And why we are emphasizing on relative oil volume, because again, as we mentioned earlier, that the relative oil volume measurements can be highly uncertain for lean gas condensate reservoirs, depending on what type of PVT cell you are using. So that's why the this forward material balance is generally not accurate for lean gas condensates. Okay, so for lean gas condensates, generally this QC is not accurate, uh, and that's mainly because of this uncertainties in the VRO measurement. Okay, so in this QC, what we will be doing, we'll be calculating, as I mentioned, the oil composition, the mole fraction of the oil phase for each component at each pressure, which is represented by K here. And for that, we will need these numbers here. We will need to know what is the total moles of what is the total moles that are present in the PVT cell at a given pressure, the total composition present in the PVT cell, the moles of gas present in the PVT cell at a given pressure. And the reported data. So if we look at this calculation here, we look at this equation, this guy here, the reported data. So among all these parameters here, the only data that we know that's reported is this yi. So all other data that's required here, the total moles, the zi, the ng values, those need to be calculated using some kind of reported data. Okay, so again, we can look at how, for example, you can calculate those parameters. Gas moles at any given pressure, okay, again, this is simple. P equals to NZRT, so we should know the pressure. We know should know the volume of the gas phase, the gas Z factor, and the RNT. Okay, at that pressure stage. So um, and then again the gas volume at any given pressure stage. So Vg at any given pressure is equal to the total volume. It should be the same as the initial volume minus uh, the VRO at any given pressure times Vs. So this should be at any given pressure K, the relative wall volume times the saturated volume. So that should give us the volume of the gas phase, because this VRO times Vs, that's the oil volume, and this is the total volume. So the difference gives us the volume of the gas phase at each pressure. And yeah, and then we have here, and we have NT, the total moles. So the total moles at any given pressure K is equal to the total moles present initially, which is NTS, which we generally assume 100 moles, like a basis for the material balance, minus the moles of gas being produced, or the moles produced from the PVT cell actually. Okay, so yeah, and then we also have ZI. So ZI, the total composition in the PVT cell at any given pressure. So it is equal to um, the total moles present initially for the given component. So that is NTS times the ZI at the J equals to 1. So J equals to 1 mean here it means the first pressure stage. So that is here. So that should give us the total moles of the component I present initially minus the moles of the moles of the component I produced, which are produced in the form of gas phase. So Yi times delta N GP. Okay, so this is from J, and you start from the like for example J2 to pressure stage K, and then so this gives us the moles of component I at the given pressure stage divided by again the total moles present at pressure stage K. So this way we can calculate the total composition, and once we have these information, we can put here, calculate this XIK. Now what we do with this XIK, which is the oil composition at any given pressure stage, what we can do is we can check the lab reported XI, which is only reported for the residual pressure stage. And again, if you don't have this data, then you should always ask the lab to give you this residual pressure, this composition at the residual pressure stage. And then you can also do this. You can compare the lab reported XI with the calculated XI value at the residual pressure stage. So that's one comparison you can do, and you can also check whether there you have any negative moles, more negative mole fractions calculated at any pressure stage, because you know the oil composition cannot be negative. And what you can also do is you can actually calculate the K values, because K value is just the ratio of Yi to Xi. Yi we know from the lab, and Xi we have calculated, so we can calculate Ki and then plot the log of Ki versus log of pressure. And then once you have that plot, you can see if there are any crossing of the K values. Okay, and that's something we will see in the Excel file, like how the plot should look like, and what do we mean by crossing, for example. So that's what you can what you can actually check in this material balance. So one important comment about the forward material balance is that if you don't have in the PVT report, if you don't have this residual oil composition reported at the last stage, you can do the entire CVD material balance, this forward material balance calculation, and you can calculate this residual uh, residual oil composition from the material balance, and you can calculate this Ki values and then check for this crossing of the K values. So you can still do the material balance. What you will not be able to do there, the forward material balance, that you will not be able to compare the calculated residual oil composition with the lab reported residual oil composition. But that's not the most important thing in this forward material balance. You see, the most important thing is that you see the K value plot, and there should not be any crossing. You should not get any negative amounts of uh, for any negative amounts for the calculated residual oil composition at the last stage or even at any pressure stage. And if you have that, if you have any crossing or these negative amounts, then it represents a bad QC. But in the backward material balance, when we discuss that, you need to have this lab reported residual oil composition, because that is the input to the material balance equation. If you don't have that information, you cannot perform a backward material balance. And we have already discussed that the backward material balance is generally more important than forward material balance. And that's why you should always ask the lab to report this residual oil composition for a CVD experiment if they haven't reported it. I guess so this was all on the theoretical side again. So we now jump to the Excel file and try to implement this material balance in the Excel spreadsheet. Okay, so we go. Yeah, so we did the backward material balance, and now we can try to do the forward material balance. So again, all the data is there. It's the same as in the backward material balance. And again, this data is missing here, so we just copy it from here. Because we discussed in the backward material balance that this is given in the lab PVT report. This data here, the relative moles produced. So we just copy it here. And you can also see it in the lab data. So this is the PVT report, and these are the values that we should have in that row. So now we have that information here. Okay, so again, first step, calculating NP and delta NP, and so you have again started with the basis of moles, 100 moles initially. So we can do this calculation again, and then also divide by 100 because it's in percentage. So just drag this down here, and then in delta NP, so first one is 0, and because these are incremental moles produced, so this minus the previous one, and then we need just calculating the average, the gas molecular weight, the gas gravity times 28.97, the air molecular weight, So again, dragging it down, and now we need to know the gas volume at each pressure stage. And the gas volume we discussed in the PowerPoint. Uh, let's see. Yeah, so you see here the gas volume is the total volume minus VRO times Vs. So the total volumes, we haven't calculated the total volume. So here we can calculate the total volume first, which it should be the total moles initial, which is NS times the gas Z factors times the R times the temperature plus 460 divided by the pressure. Okay, so it should be the same value as we got here, 38.99, yes. Yeah, so now this gas volume is this guy here minus VRO. So we have VRO here divided by 100 times yes. Okay. We should have fixed the cells, so this should be fixed. There, yeah. So we got the gas volumes at each pressure stage. The moles, again, knowing the volume, we can use PV equals to NZRT. And yeah, so the pressure times volume multiplied by the volume divided by ZRT, Z times R times T needs to be fixed. Initially you should have 100 moles and then 7.4 moles remaining for the gas phase. Okay. Okay, and then the total moles at each pressure stage. So that should be the how much moles we have initially, and S fixing that minus sum of moles produced until a given pressure. So that is NP. Okay, so but here, since like when we should drag the formula, this has to increase, so this should be fixed, and this we can keep it changing. So that's the sum of moles produced, and I think that should be it. You can check. Yeah, that's what we wrote here. Yeah. Okay. So we have at least these numbers here, and now we need to fill out this table, which is for the total composition, and so the total composition for each pressure stage, and here we have all the pressures. So so for the first pressure stage, we know the total composition is the same as the reported composition. Okay, the composition starts to change from the next pressure. So there again we have this formula here, the Zik equals to NTS Zi. So, um, so if you try to implement that formula here, so it should be the total moles initially we had, which are these, times the initial composition or the mole fraction of the component initially. Again, this yeah, we need to fix it such that it doesn't change when we drag on the right, but it can change when we drag down. So it should be like this. So that's this guy here, NTSZI J1 minus the moles produced. So that's some product of Yi times here is the yeah, so the mole fraction of a given component uh, times yeah, so it should start from this and then also this and then it should be fixed because this sum here this should be from J yeah so J2 to K, right? So J2 will be fixed, so that's our second pressure stage and so that should be fixed, and then we have to, and again if we are fixing this, then we should allow it to change when we are dragging down, but not if you're dragging on the right side. And then this one should be allowed to change. So that's the mole fraction times the moles produced. So delta NP, this guy here. And again, it's the same concept here. You need to do this times, and then try to fix this one. Okay. And then divided by the total moles. So at any given pressure, which we have already calculated, and T, this number here, and then try to fix this. I think it should work. Let's see. Yeah, so B4 is B4 is the total moles, yeah, and then we have B9, which is the initial mole, and then we have minus uh, some product of this the mole fraction times the yeah, so the mole fractions times the moles produced, and Oh, okay. Yeah, so we should have fixed this because we don't want this one to change when we drag down. That should be like this. And then let's see 28, which is total moles again. We don't want it to change when we are dragging down, so that should be this. Let's see if we are done it correctly. No. Okay, what's going on here? So this is doing correctly. This one is not doing correctly. This is okay. So there is something wrong when we have this delta NP to C24. So C24. Okay, so we should have fixed that. Okay, so I think that looks reasonable. So we just drag it here, and then we get, and here we can just say, okay, that's this composition here. Okay. So just do a bit formatting. Okay, so the next step, once we have the total composition, the next step is to get the equilibrium oil composition, which is this formula here. You know the total moles, the total composition, the gas moles. Okay, so let's try to implement that formula. So NT, that's the total moles. That should be fixed like this. Okay, and then times the total composition. Yeah, and then minus the gas moles. Fixed like this times the mole fraction of the gas phase divided by NT minus NG. So NT is this number here minus NG, which is this number here. Okay, let's see. So we should not have any oil composition. That should be oh. Yeah, we should not be calculating it actually there. But let's see what happened here. So we have the total moles and NTZI minus NGYI, and then that should be 0, right? So NT, let's see what happened here. NT CI minus NG, just B10. B32. So B32 and B10, they are identical. And then B28 and B27, they are identical. That should have used it. Should be 0, right? So when we are doing this calculation here, so this numerator b28 minus b27 means it should be 0 and that should be 0. Yeah, but maybe it's because of the 73.191. That's strange. Why that composition? For this component nitrogen, why do we have a composition? Because the this numerator, it is b28 minus b27, that should be 0. Okay, and then this is also 0. b28 and b27 and b32 and b10 are the same. b32 and b10 is nitrogen, b32 is nitrogen. Understand? Alright, let's move this formula to the right and see. So we got reasonable numbers, so we can just okay, so yeah, we have the oil compositions at each pressure stage, and then we can calculate the K values at the we can calculate the K values. So that's yi times yi divided by the calculated xi. Again, this calculated K values should be undefined here. But though, yeah, so we should be looking at the K values at all these pressures. These are not the important ones. Yeah, so we have calculated the K values, and what we have found when we calculated the equilibrium oil composition, that we don't see any negative mole fraction, which is a good sign. K values are also there, and what we can also do is we have calculated the equilibrium oil composition at all pressure steps. So we can compare this equilibrium oil composition at the last pressure step with what the lab has provided to us. So this is what the lab has reported, and we can look at it here in the report. Actually, That's what the lab has reported, 9.17, 72.09. So yeah, and you see that it's almost spot on, which is very rare to see in forward material balance, that you get very good match of the final stage oil composition. Because no matter how good the PVT cell is and how diligent you are in measuring the PVT data, there is always some uncertainty in the measurement. Uh, so compositions and relative oil volume, so you don't get a perfect match. The reason why we are getting a perfect match here is again because this is like synthetic PVT data. And if you look at the K value plot, so this is log of KI versus log of pressure, and that's how perfect forward material balance K values look like. These are for all hydrocarbon components, and we were discussing what do we mean by, like, when we look at the K value, what we are looking for is that how the K values are behaving, and are if there is any crossing of the K values. So what do we mean by crossing is, for example, we know that, for example, this guy here, that is C6. So this is let's just try to go over, and then add a page, I guess. We just have added a page. Should not be here. Page, insert page. Okay, and then we can, let's see if we can copy this. Yes. Whoa, very nice. So we have the, so when we were saying that what do we mean by K value crossing? So let's suppose this is C6, right? So this guy here, C6. So the K value of C6, so this guy here, this is C6, and this is, for example, IC5 or NC5. So that's NC5. So what we would like to see that the K value of, for example, NC5 component, it should always be higher than the K value of C6 component at all pressures. Okay, so it means that they should not cross. That's what we mean by K value crossing. So we see if there are any crossing K values between any two components. So I think that was it on the CVD forward material balance, and then we will jump to our next topics on the material balance on DLE and separator test.